Hello and welcome back to another episode of Math with Son. Today we're going to be starting rotational kinetic energy, which is a pretty big doozy of a lesson. So we're just starting it today. So basically, by itself, it's not that bad. We got kinetic energy of a rotational object is equal to 1/2 its moment of inertia times its velocity squared, which is very similar to 1/2 mv squared for what we've dealt with before. Now, the thing that does make it more difficult is sometimes objects that are rotating are also moving horizontally or linearly as well. Okay, so when that happens, you have both translational and rotational motion, such as a wheel on a car. Newton's laws for rotational mechanics still remain valid as long as the axis of rotation passes through the center of the mass and the rotation does not change its direction, because if it's changing its direction, then we have some other forces acting upon it. When you have a rotating object that is also moving linearly, you can find the total kinetic energy by just adding those two things together. Okay? So we got a few examples that are going to connect rotational and linear motion. And then in a different video, we're going to go into like some deep examples. So the first example that we're going to have is going to be a soccer ball with a mass of m and a radius of r is rolling at a speed of v. Find the total kinetic energy given the moment of inertia for a solid sphere is 2/5 mr squared. Okay, so remember we just had for kinetic energy is equal to 1/2 that moment of inertia, velocity squared, plus 1/2 mv squared. Notice how we have angular velocity and we have linear velocity. In order to simplify things, we are going to convert one into the other so that we can actually combine some like terms here. Because to be honest, this is pretty easy. We could just plug in the 2/5 mr squared for the I and you could call it a day. So your total kinetic energy would be 1/2 of the 2/5 mr squared times the angular velocity squared plus 1/2 mv squared. Now, typically that's correct, but we're going to want to try and simplify it a little bit. So a while ago, we learned that v is equal to the radius times that angular velocity, omega. And if we know that v is equal to radius times the angular velocity, you can either plug in that for v, or you could solve this for angular velocity and find out that v over r is equal to the angular velocity. You could do either one. All right, it depends on what you would like it to be in terms of. Since this is rotational motion, that's what the video is about, let's keep it in angular velocity mode. All right, so that means k would equal 1/2 2/5 m times r squared times, we are going to be converting angular velocity into v over r. So this would be v over r squared plus 1/2 m v squared. So I guess I'm keeping it in terms of v, linear speed. Why not? So with that in mind, you can square the v and square the r. You'd have 1/2 times 2/5, which ends up being 2 over 10. 2 over 10 is 1/5 mr squared v squared over r squared plus 1/2 mv squared. Running out of room, but you have v squared over r squared, and the r squareds would kind of just cancel out. And if you cancel out the r squareds, you have 1/5 mv squared plus 1/2 mv squared. And if you add 1/5 and 1/2 together, using probably a calculator, you end up with 7/10 mv squared. So for this next example, we're going to have a yo-yo that is essentially just dropped from somebody's hand. And when it is dropped, you have the gravity pulling down on the yo-yo, but you have the force of tension on the yo-yo string kind of pulling it up. So what's happening here is that gravity is pulling it down, which would be m times g, but the force of tension would be pulling it up. All right, so with that in mind, you would have this linear momentum going down, but you got this rotational energy that is pulling it back up with the force of tension. And in order to do this problem, you have to recognize what is actually happening in the linear perspective first. That to me seems easier. So the sum of all forces in the linear direction, which is the up-down part, would typically equal its mass times acceleration, but its mass and acceleration this time are dictated by gravity and the force of tension, which would be mg minus that force of tension. Okay? So, with that in mind, we need to figure out, we know what mg is, that part's simple, but we need to figure out what is this force of tension. And that force of tension is dictated by rotational energy. All right? So, that rotational energy is in the form of torque, and the sum of all torque would equal its moment of inertia times its angular velocity. And we are essentially asked to find the acceleration of this yo-yo and the tension of the string. I'm hoping you've been reading the question. So with that in mind, torque is equal to essentially its tension, the force of tension, times the radius of the yo-yo. And the I, which would be provided to you, but you're assuming this is a massless string, and you have a mass at the end of it known as the yo-yo, and that would equal 1/2 mr squared from our a moment of inertia formula sheet of list of common things. Your angular acceleration we're going to want to relate to a linear format. So the angular acceleration is equal to the radius dividing the acceleration. Excuse me, it was acceleration is equal to radius times alpha. And if you divide by radius, you end up with your angular acceleration. So we're going to substitute that in as well. We're going to substitute in the a over r, your acceleration divided by radius. Now we're going to do a few little calculations here. We're going to simplify and see what happens. First things first, one of these r's will cancel. But also here we have the force of tension, which I'm going to write as Ft, F sub t would be better, times radius, because that's what torque would be. Well, the radiuses would cancel out there because we had a single r and a single r there. So you essentially have the force of tension that is equal to 1/2 ma. That's convenient. Now we can plug that back in over here, and if we do that, we find out that mass times acceleration would equal mass times gravity minus 1/2 ma. We're getting closer to figuring out what the actual acceleration of the yo-yo is going to be in the downward direction. So all of these have a mass that would cancel out. Plug that in over here. We end up with acceleration is equal to g minus 1/2 of acceleration. We need to add that 1/2 over. If you add 1/2 to 1, you end up with 1.5, or 3 over 2a is equal to g. And then if you solve for acceleration, you would end up dividing by 3 and multiplying by 2. And you would end up, if you divided by 3 and multiplied by 2, you would end up with 2g over a. 3a. Oh my gosh. Over 3. There's our acceleration. All right, that's convenient, because second part is find the tension of the yo-yo. Well, we already have that formula. It's 1/2 ma. So the force of tension would equal 1/2 the mass times its acceleration, which would be 2g over 3. And if we do that, the 1/2 and the 2's would cancel. You would have the force of tension is equal to the mass, the 2's canceled, times gravity divided by 3. Okay? Well, that's going to do it for this one. Until next time, everybody, stay positive, and I will see everybody later. Bye.